we were originally scheduled, Rick and I, to give a talk entitled "When Did Plate Tectonics Start?" But our enthusiasm for doing this was considerably diminished when Jeroen got up last week and gave a talk entitled "When Did Plate Tectonics Start?" So what we thought we would do is, in fact, given the seeming enthusiasm of a large group of us, to do a project related to continental evolution. And by the way, if some of you are unfamiliar with this term here, I believe seismologists refer to this as the top of the upper mantle. So what we thought we'd do is take a romp through the history of continental growth models to really emphasize the strengths and the many weaknesses of these sorts of speculations. And we'll begin by, I think what you'll see is that, in my view, and Rick can speak for himself, but I think that the state of the art is that we need to unlearn a lot of things that we thought we knew about continental growth before we can begin to really make progress in understanding it truly. So we're going to start to talk with just a brief connection between Earth's heat loss and plate tectonics that hasn't been addressed yet, just for completeness, and its relationship with possible early continental growth. Then we'll go on to the main part of the presentation, which is in fact an interactive experience with audience involvement in choosing which of the very large number of continental growth models we'll focus on. And as we wind that up, we're going to introduce a mystery guest to step forward and talk about his recent entry into this fray of continental growth models. Then we'll talk a bit about broadly shared assumptions of the composition of the Earth's crust that and their plausibility. I'm then going to hand over to Rick, who will make a few comments of his own and expect to be interrupted with questions. But this I'm not sure this is all going to take 40 minutes or it's going to take 2 hours. So it depends on how enthusiastic the group is during this interactive spell. Okay, now let's really take a step out of here, back to our conversation about heat sources and sinks. Remember, we've seen this relationship that the cooling or the heating of the Earth is simply the heat sources minus the heat loss. And here's a very schematic. It doesn't matter the shape of these curves. They're not meant to imply anything other than to provide a little topology to try and make the point. But let's imagine that early in Earth history, that melt extraction, that you make a magma ocean, you have advective transport of buoyant magmas, that convection with different modes provides an efficient way to bring the Earth's interior heat to the surface, and that conduction is this, in fact, predictable but slow mechanism for cooling the planet. So the history of the planet, the total heat loss as a function of temperature, remember there's no time implied explicitly in this slide, is the lime green curve here. At the same time, the planet will have some heat production of some value from radioactive and other sources, and that will change through time. So there'll be times when the Earth is cooling, heating, cooling in a stable fashion, where there's essentially a positive feedback in the assumption of the relationship between convection and internal heating, and other times where it's unstable, leading to if you run time backwards, which is very hard, but if you do it numerically, it leads to what you've been told is the thermal catastrophe. Okay, so now let's look at imagine that in fact instead of that sort of continuous relationship between heat loss and temperature, there was discontinuous transitions between these various mechanisms. So here's melt extraction, plate tectonic convection, stagnant lid convection, which has been introduced to you, and conduction. So the point I want to make here, and in fact, and there's heat production. So let's actually keep heat production at this level And imagine you start a planetary body at high temperature such that the fastest way to get rid of heat is to advect magmas towards the surface. And as a result of that, the planet is going to cool. But the question is, when it gets to this threshold, is there a discontinuous transition to another mechanism? Do these things operate happily simultaneously, or in fact you move to a whole different mode of heat loss? Now, because the heat generation is greater than the heat loss by this mechanism called plate tectonic convection, the planet's going to heat up, and the question then is, as it heats up, will it in fact get to a temperature where a different mode of heat loss is introduced, and around we go again. Eventually, of course, with time, this heat production, if it's radiogenic heat, will diminish. And the whole point of these two slides is to introduce Sleep 2000 to you, which is a less colorful version. I'll take you through this just in a couple of minutes. But again, here's global heat flow. Here's mantle potential temperature. And imagine we start up here at very high temperature and so hot that, as David told us, there's a global magma ocean. Eventually the planet cools, and at this point there's a discontinuous, it freezes, a magma ocean freezes up, and there in fact is a discontinuous transition to some other mechanism. Sleep speculating that it could be, in this case, plate tectonics. So we drop from this high heat flow at the latter stages of magma ocean crystallization down to here, to D. And because in the early Earth, here he's characterizing Hadean heat production as being relatively high, so the Uri number is greater than 1, we heat up. And eventually, perhaps because we're heating up, we're melting more of the mantle, the plates are getting thicker, they're hard to shove down, plates are moving slower, and the mantle starts to heat up excessively to the point where the plates are now so thick they won't go down the trench. It locks. We no longer have this effective mechanism of heat loss, and boom, up you go back. So his speculation is that we might have run around this cycle 3 or 4 or half a dozen times early in Earth history, that the magma ocean of which we talk about, for which we have no geochemical evidence of its existence, might have been the last of a dozen such events. But eventually we settle down. Now here's present radioactive heat production, and Norm characterizes our position here with a Uri ratio now less than 1. Here we are heading for ultimately ridge lock, where, for example, as you see in the Southern Ocean, there's amagmatic sections of the ridge. Eventually, the potential temperature will be low enough as to lock the plates up, and then we go into this stagnant lid. But in fact, that could, given the sufficient internal heat generation, put us into another cycle. So I just wanted us the week not to end without us talking about this. So the question is, do such...
Well, because of the reason that we would draw such a diagram in part owing to our lack of imagination for other convections that exist above the plate tectonic regime in that diagram.
Give me an example. I mean, I have a lack of imagination regarding this. But sure, I mean, whatever if there is a hidden or an unknown.
For you, but the sort of heat piping that happens in Io, isn't that a plausible intermediate regime in the very early Earth just after the magma?
It would be a modified stagnant lid.
Yeah, but it would sit between plates and magma.
Oh yeah, no, this relationship here is essentially arbitrary, right? I mean, why not?
Well,
yeah.
My point is that there could be principally solid convective regimes that, in terms of
solid.
heat flow, would plot.
Oh, okay. By solid, you mean fluid? Yeah.
So Io, of course, has a very, very high heat flow, actually higher than what he's putting in for Hadean. It's enormous, about 2,500 to 3,000 milliwatts per square meter. And we know for sure that the outermost 100 kilometers or so of Io is mostly solid. The way we know is because it's got huge mountains all over the place. And so some people talk about magma ocean underneath that, but it's not what people normally
Well, something's molten somewhere.
So I would say there could well be a regime between what he means by magma ocean and the trench and the plates.
Yeah. Okay, so these transitions exist. It's worth speculating, but it hasn't really, it's in that realm. Okay, now on to the main course. What you're seeing here is not an exhaustive compilation of continental crustal growth models over the years. So what you're looking at here is the relative percent of continental crust volume relative to present day, 100%. So here we are at 0 time. And you got a log scale. Here's time since first solids, and here we are ticking through geological time. Okay, and you can see that most but not all the parameter space is taken. So for you students, there's still some, or some zigzag trajectories are still possible. But this is was a moment in time. If you look at these, there's 13 different models here, and we can talk about all of them if you've got the Constitution. But if you notice that between 1978 and 1989, 10 of these 13 models were, the 1980s were the heroic era of speculating about continental crustal models. And once your neighbor did it, it was, irresistible for you to, enter into the fray. So what I'm going to do is I'm going to go to really the first. Hurley and Rand came out in '69 on the basis of essentially some strontium isotope arguments about the seawater and the continents, but mostly using potassium argon ages. And for those of you that don't know, this is a great way to date an undisturbed flat-lying, volcanic horizon from the Cenozoic, but not a great way to characterize a rock-forming age in the Archean. So we'll go to Hurley and Rand, and then I'm going to go up to Armstrong et al. 81. So we'll go from, in fact, this bound here way up to essentially no early crust and very late growth of continents. To the idea is that I think the red colors I think you could characterize as the lunatic fringe over the years. That this was pretty sparsely occupied territory until relatively recently. Okay, so let's in fact go to Hurley and Rand. So you see their growth curve here, and they were the first guys to do this. Potassium argon ages. They looked at distribution. Now it's 1969. We've been dating rocks by this method for almost 20 years. There's a global database, and it was very tempting to imagine that these age patterns could somehow represent when continental crust arose. Now, we've got to be careful here because in addition to the fact that the potassium argon system is very fragile, okay, argon, the daughter product, is a noble gas. It doesn't want to make compounds in silicates, so it can easily be lost at temperatures between a few hundred and, say, 500 degrees. So in order to relate a potassium argon age to the age of the growth of continent, you're going to have to hope that you've been spared sort of the thermal rigors of continental evolution. In addition, that age may or may not be when juvenile material was transferred from the mantle into the crust. We wouldn't really have a great parameter for that until the late 1970s when the neodymium technique was developed. So they were aware of things like continental drift. So by '69, plate tectonics was firmly established. And so what they did is they simply made a histogram of what they thought were age provinces. And there weren't too many rocks known in '69 to be over about 3,800 million years old. And as you went towards the present day, say the last, they've excluded the last 500 million years, but they saw this generally increasing, kind of exponentially increasing distribution, and thus their curve here shown sort of as this, well, on a log plot, this exponential growth. Not exponential, sorry, it's linear. Looks exponential on the log plot, sorry. But the problem is that potassium argonages are unlikely to record continental growth. So you see in the subsequent histories we look at. So let's go back here. And now let's look at Armstrong's model. Okay, he wants between, say, 4.4 and 4 billion. He wants to grow the continents to something close to their present mass, and then seemingly have a feedback mechanism that retains constant continental mass since almost 4 billion years, in his view. Philosophically, he sets the paper up by saying, look, the moon differentiated quickly. He inferred that Mars differentiated not only a core and a silicate mantle, but a crust as well, and an atmosphere, and perhaps a hydrosphere. What was wrong with the Earth? Why was it so retarded that it wouldn't, in fact, create a highly differentiated crust? So the evidence that he marshaled, and I should say that he wrote a remarkable paper in 1968 that set out essentially what we're now calling geochemical dynamics, where, understanding global tectonics, he recognized that if continental sediment could be accessed through the subduction process into the mantle, that the mixing of those two reservoirs, the complete mixing, in fact, would erase a prehistory. So he was very aware of the danger of saying, well, since I can't hold, we haven't found a rock that's 4.2 billion years old in my hand, he resisted the temptation to say, since we haven't found it, it never existed, which I would actually characterize as sort of the community standard. So he noted that the continental crust appears to be uniform with age, that if you look at the thickness of crust over the last, say, 3 billion years plus, it's about 38 kilometers thick. And this is not a particularly strong argument, because this is what the crustal thickness looks like today. Who knows what it looked like at 3 or 2 or 1 billion years? This is more a statement of isostasy. The constancy of freeboard. This is a very simple concept made very complicated by a sequence of authors over the last 30 years or so. And that is simply that if you can go back in the geological record and let's say you find a beach deposit 3 billion years ago, well, that means that at least that part of the continent was sticking up above the ocean. So imagine this planet with one ocean, okay, worth of water, and no continents. Well, clearly no continents are going to stick up above sea level. Now you put 5% of the present mass of continents into that Earth's surface, and depending on how it's distributed, okay, how you want to distribute that continent, it's unlikely that you'll have any subaerial exposure. So you have to get a certain minimum amount of continent before you, in fact, can have the bimodal hypsometry that we know today. So in effect, what he's showing here is, at least through the past 2.5 billion years or so, and arguably earlier, the geological record contains evidence that continents were poking up above sea level. So obviously, here we're assuming that the volume of the ocean hasn't changed, that we haven't, in fact, either had a net loss of water through the subduction process in the mantle, or degas, or material visiting us from outer space. So there's a bunch of assumptions here. And I'd have to say, in conclusion, that this has been just a gigantic red herring, that you can make a zeroth order statement about the fact that at least in various places continents were sticking up above sea level. But there's so many variables. For example, Reymer and Schubert said, well, Armstrong was generally right. We might talk about that later. But early on, when the mantle was hot, the ridges would have stuck up higher, would have displaced oceans onto continents. So in fact, there must have been less continent. Armstrong responded, oh no, but the mantle lithospheres are growing slowly with time. They're pulling the continents down with time. They were actually more buoyant. Many of these things are currently unknowable, so it's really been a red herring, as I said. Here's something, though, that he emphasized in his 68 paper, and that is that if you look around the world and you say there's material coming indirectly from the mantle through subduction of oceanic crust, that's adding new material to the continents. You can see it happening in the Mount St. Helens. You can see it happening in any arc. So if you can estimate how much arc magmatism is occurring, and then how much sediment is being subducted, so-called subduction erosion. I'll show you a slide. Well, I'll show you a slide right now. Okay, so imagine here's a convergent margin. Here's the downgoing plate. And adjacent it, you've got a accretional prism here. Sediment, in fact, in some origins, is being accreted. Okay, you have a subduction zone in which sediment, it's an accretive origin, and others that are, in fact, erosive, that the sediment, in fact, begins to interact with the upper plate here. Rock transformation occurs, essentially cementing continental sediment onto the downgoing slab. It's insufficient in volume to really interfere or influence the buoyancy of the whole system. So, but this continental material is carried into the mantle, where if it's well stirred, eventually it will erase evidence of its prior existence on a continent. And what's interesting is when Dick wrote this paper in '81, the estimates of tectonic erosion were about 0.2, 0.3 cubic kilometers per year. And many people, I think Bob Kay, the principal one, want to, in fact, define 1 cubic kilometer per year as the Armstrong unit. So you can either grow continents 1 cubic kilometer a year, but back in the 80s, the estimates were much lower than present day. Dick saw the evidence as essentially indicating that today we're about in equilibrium, that as much arc magmatism, as much mantle material that's being introduced into the crust, okay, is exactly balanced by what's in fact going down the chute back into the mantle. And if that's true, we're at steady state, that we've either been growing or shrinking, and he thought it behaved the same way it is now over the past 4 billion years, that argued for the crust having as much mass today as it did 4 billion years ago. He pointed out that at the time, the late 70s, early 80s, a number of geochemists, and maybe we'll trip across those models as well, were arguing that the strontium and neodymium isotope correlation that Rick showed you last week argues for a rapid growth of continental material at about 2.5 billion years. And his point was that if the Earth is behaving in the past as it manifestly is today, i.e. we're making some new arc material and we're destroying continental material in an equal balance, then the isotope record is ambiguous. It's equally consistent with recycling as it is with, as interpreted by others, slow growth since about 2.5 billion years. He did at the time was a sophisticated computer model. In fact, is a computer model of simulating continental growth, in which he made 100 imaginary crustal boxes and 100 upper mantle boxes. And then said, well, in the past, as in fact was advocated by many dynamicists, Jeff Davies particularly, that plate velocity was proportional to the square of the heat generation. Remember, heat generation 4 billion years ago, 4.3 billion years ago, probably 3.5 times or so what it is today, so that his argument was that you could scale the plate velocity as the square of the heat generation. So if he was going to simulate crustal recycling at a plate boundary, he would do it 10 times faster 4.5 billion years ago than the model would be encouraged to do today. So here's the Hurley and Rand model, which I think you'll find here in the darker of the two blue colors. And I think you'll see later that, in fact, this is no longer anybody's conception of what the preserved geological record is. And here was his model results, shown in the dark blue line. And he thought that this was pretty good agreement. So he, in fact, had shown that it's physically plausible to explain the age distribution and the isotope distribution, although, in fact, he failed pretty spectacularly reproducing the lead-207 of mantle-derived volcanics, although every other geochemical model fails spectacularly to explain the lead-207 204 ratios of mantle-derived materials. Okay, so no questions? Let's go back to the beginning here. And we're open for suggestions. You guys, shout it out. What do you want to hear? Pick a model. We're not going to do all of them. But I think, say what? McLennan and Taylor. Okay, well that's not a great place to start. But it's up to you. Yeah, this is a weird one. This is something that not only has no other geochemist been able to explain to me, but I've spoken to the authors, and I can't make sense of it either when I talk directly to them, because what they're arguing is that knowledge of only trace element concentrations and ratios can tell you what the magnitude of continental crust was as a function of time. Okay? So what they're looking at, in fact, let me show you sort of an example of the kind of data they're dealing with. They would take shales, if the continent's weather and the material gets put into low-lying basins or in adjacent shelves. If you can recover shales throughout time, you've got a pretty good estimate of the average composition of what's exposed. Okay, so when they look at say Archean upper crust, simply these would be shales derived from Archean basins with shales in it. I'm happy to know that at least somebody on the planet thinks that you know the Archean upper crustal dysprosium content to 3 significant figures. But you can see that there are differences, okay? That Archean upper crust, regardless of sort of what flavor you take, is seemingly different from what looks to be remarkably uniform post-Archean trace element concentrations in shales. And there are some issues with the manner in which they analyzed the samples and things. It was not the most sophisticated setup of the day, but their arguments are independent of that. So what they argued is that they don't see significant changes in post-Archean shales, but there is this clear difference. And if, in fact, to explain, okay, the getting rid of this signal here, okay, that if this signal was characteristic of the Archean upper crust, then you would need, in fact, to have 4 times as much post-Archean crust in order to, in fact, get rid of that, this, well, in fact, low concentration or mafic signal. These ratios were more consistent with a mafic source. So their argument is that the Archean crust prior to the Proterozoic was more mafic than subsequently. As Kevin Burke pointed out, however, most of their shales come from greenstone terrains. So in fact, it's pretty much what you'd expect if you're just shedding off a greenstone, that the compositions are going to be more mafic. So there's a preservation bias and a source bias in there as well. So their argument then, they make, and I haven't been able to follow, is that somehow, let's see, here's McLennan and Taylor, that somehow these trace element concentrations and ratios permit you to make a statement about the magnitude of crust. And my sense is, and maybe Bill's got an opinion here, is that they were influenced by other models of the time. They were influenced by O'Nions et al. And by Allègre, who were interpreting the strontium-neodymium correlation from mantle rocks as evidence that there was rapid growth in a sigmoidal fashion. If we look at Allègre, we'll see that, indicating that rapid growth at around 2.5 billion years. Okay. Hit me. Allègre, yeah, it's highly relevant. Okay.
Divide these more into inventories, simple geochemical inventories versus mechanistic models. We can make more informed choice here.
You know, they all have their own quirks. I mean, how would you characterize McLennan and Taylor? It's tough because, you know, they're using trace elements, but ultimately they were influenced by, in the form of their curve, by someone else's assumption about the relationship between strontium and neodymium isotopes and
Reymer and Schubert is the one I can think of probably forward model.
No, not so. They actually they were okay. We're back in. Okay, here's Allègre. It was a box model. Rick, you feel free to chime in any time here. The correlation between strontium and neodymium, Rick showed last week, well known. Claude was, introduced this sort of engineering concept of an average age, and if you look at the continents, you'll see that the mean age from neodymium model ages is about 2.5 billion years. We don't see rocks prior to 4 billion, so it was, it was elegant or simple to produce a sort of this sigmoid, which predicted rapid growth when, in fact, you look in the Slave Province and you see lots of rocks forming around 2.7 to 2.5 billion years. So that sort of made sense. And the view that, if you look at the rate of arc accretion over the past 400 million years or so, 500 million years, it looks about co-equal to what's getting eroded down the subduction chute. So that's pretty much it. So we all agree that the neodymium model age is about 2.5. But the question is, did it arrive there by some complex relationship or this simple sigmoid?
So these numbers in comparison to the isotope evolution have a lot to do with what we're going through in our mass balance model. This is a time period, basically all these models, McLennan, Taylor, Allègre, even the Armstrong for that matter, were being done in the era when we thought there was a geochemical balance in the lower mantle.
Oh, absolutely.
So what the isotope system,
which we thought the seismologists were telling us, or the geodynamicists were telling us. It was a negative feedback.
Well, there's a feedback here between looking at the amount that the mantle was depleted by continental crust formation, but your answer to that question depends on how much mantle you're depleting by crust formation. So all of these were based on just the upper third of the mantle being depleted. And it ends you up with a different result. The other thing that feeds into this is the question of what the bulk Earth composition is. These were all starting from a model that had a chondritic samarium-neodymium ratio for the bulk Earth. So an epsilon neodymium is 0 by definition, whereas I showed you in my talk that bulk silicate Earth value could be as high as +8, in which case continent formations really had a very small effect.
Right. Okay.
So, Mark, why have people stopped doing these models now?
Well, I think parameter space is largely filled.
Because space is being filled.
Yeah.
An unsolvable problem, or?
Well, as I said, you may get the sense when we're finished the talk that I'm a bit pessimistic, that I think we need to step back from a bunch of assumptions we make about how the crust is formed and therefore what its composition is before we can really step forward. So you, Quentin, you want Reymer and Schubert. And so, in fact, they did a very systematic, I mentioned that, that Allègre had low growth over the past 500 million years or so because of the recognition, at least the zeroth order recognition, that arc magmatism and subduction erosion might be about co-equal in this period. So these guys actually went in and they looked in great detail at Phanerozoic island arc growth rates, and they were pretty comprehensive. What they didn't do was look at the isotopes in detail. So what they're assuming is if they see that there was an arc or a collided arc the last 500 million years, everything in that volume of arc is assumed to in fact have been transferred from the mantle to the crust, when in fact possibly that's true, but possibly 50 or 60% of it, in fact, could be reworked continental crust and not represent growth. They assumed, as Dick did, the more rapid, Dick Armstrong, rapid growth in the Hadean and Archean. Here's the Reymer and Schubert curve here. So they're happy to have 40% of the mass of the crust at 4.3 billion years, but notice that it's sort of systematically less than Armstrong. And again, this reflects the fact that they thought that freeboard, well, first off, there's no freeboard constraint at 4 billion years, but in fact that the different thermal structure of the planet then would require that there would be less continent in order to have the ocean basins sitting nicely between the hypsometry. Considered hotspot additions, so they were looking at also oceanic plateaus and other hotspot plume related objects. This was I think they were in the forefront of this. Armstrong, for example, not considering the possibility of underplating or hotspot addition. So again, that the freeboard, in fact, would actually require that the ocean basins deepen with time.
Of course, all these curves have to go to the same point at the end, but they come in at very different gradients, and I would have thought that since that pertains to the current state of the Earth, that there should not be so much disagreement. Yeah, remember, the problem with doing, I've tried to, for this was a review paper on the Hadean Earth. Yeah. So this is convenient. If you actually look at this in a linear fashion, there's 2 billion years, there's 1 billion years. So these are very flat, actually, over the last 2 billion years. All of them are? Up here,
yeah, all these guys. It's just difficult to yeah, Gabby.
Didn't pay attention, but the one that obviously sticks out very much is this Fyfe model, and so that even implies that we lost some continental crust, right? So what makes this one?
He thought that subduction erosion. Well, let's go to Fyfe. Here it is. Yeah. He thought that. That they, in fact, the subduction mass balance indicated that the continents were shrinking, that we're actually stuffing more continent down the subduction zones than was being generated by.
Is there any evidence that continents actually subduct?
The continent material would subduct. The sediment derived from a continent. Clearly, continents can make their way down a fair distance, but they tend to bob up if you keep them intact. But if you make fine-grained sediment and then essentially lithify them to the top of the downgoing slab. And he also argued higher freeboard. He in fact he wanted more continent in the past to explain that. I actually don't recall. Sorry. Also, he did want to subduct water, so his ocean was variable. There's a high degree of speculation in this. Part of it I think was just let's lay claim to some parameter space that hasn't been occupied before. Okay, we can probably do one more.
Next question.
You just did.
Yeah. Ask another? Oh, whoops, just did.
You may ask 2 questions.
Okay. Do any of these models, and you can tell me if this is a irrelevant question or not, distinguish between an upper crust and a lower crust? Have a differing age distribution to the more maybe lower crust and the upper crust, which is certainly sink, which is certainly alluded to in the
No, to my knowledge, not a different age distribution. But as you saw, the McLennan and Taylor assumed that the lower crust was more mafic than the upper crust. We're going to talk more about that actually in a sec. But okay, we satisfied? We're starting to get the flavor. Rick, do you think there's anything? Oh no, wait a minute. Let's talk about Campbell 2003 because Somebody want to suggest that? Okay, yeah, this is the most.
Hey, Mark, why don't we look at Campbell 2003?
Thank you. This is an idea, in fact, inspired by Al Hoffman. I think maybe he's late 70s, right? Or that, as Rick showed the other day, he's going to show again today. When you melt the mantle to make morb, you don't fractionate niobium or titanium from uranium or thorium, but there's something about taking the oceanic crust or mantle-derived basalt and turning that into the continent or into an arc that strongly enriches uranium and thorium over niobium. So there's a fixed amount of niobium, uranium, thorium on the planet. Then if we know what the primordial value is, and we know what the modern mantle is, what the modern depleted mantle is, then the ratio of thorium, niobium, or uranium, niobium is a measure of how much of those continental goodies that were in the pre-depleted mantle have been taken out and put into the continent. So however you make a continent, whatever it is that fractionates uranium, thorium from niobium, there's a fixed complement, and therefore, if you go back in time, as Campbell did, and you look at Archean basalts, okay, so here's niobium, uranium. The chondritic value is down here at about 32, Bill, okay, and the modern ocean island basalts and morbs are up here close to 50. I think 47.5 or something is what he used. So in fact, you can read off over here the amount of continent that has been extracted. Okay, if you have a ratio of 40, okay, that means that you have to have taken 50% of the continental goodies out of the mantle, out of at least the source that's depleted to present morb values, and turn that into continent. So he was looking at samples from 2 to 3.5 billion years. And it's a lot of scatter, but when you average them, they're not obviously all down here, okay? And so when you average them here, the average Archean is about 65%, something like that. So you look at Campbell's growth curve, he's happy with a little bit of a continent in Hadean, but by 3.5 billion years, yeah, there he is. He wants 60% continent. It's just that simple. Pretty cool, eh? Except Collerson and Campbell, a couple of years earlier, did the same analysis, and I'm not showing you their original data, but what they found, and this is now translated into percent of the present mass of crust, at 3.5, remember, Campbell, on the basis of niobium thorium, wanted 60% of the crust. Collerson and Campbell want 2% or 4% or something like that. And the difference is simply, you go back in time, these mafic rocks, they're not all that happy. There's a lot of alteration. There's bad things can happen to these rocks. The variance is high. And in this case, it depends how you average these old rocks. You can emphasize a terrain that has, I see you're nodding your head, Bill. If you choose to make an average emphasizing values closer to 30, you're going to get this very low fraction. Ian Campbell was looking at, I think he was emphasized South African and Australian mafic rocks, and his average was sort of more up here. So despite the exquisite systematic look of their curve here, the same method could yield values as high as 60 or as low as 5%, something like that.
Mark, these ratios, these trace element ratios also suffer from all the issues that I mentioned with isotosis. They require that you make an estimate of the bulk silica or thorium ratio that you're beginning with. How much of the mantle has been depleted by crust formation will affect the amount of that thorium ratio change because of that. And what else? The average thorium ratio of the continental crust, which is not a well-known number either. So all of these issues sort of feed into shifting these curves up and down depending on your size.
Yeah, and in fact, when Rick takes over up here, he's going to show you, refresh your memory as to what these patterns look like. Okay, I think now look at there's a little blurb on all 13 of those mechanisms. It's there. It'll be in the CIDER file, so you can go through that at your leisure. But let's actually now move on. We have a special mystery guest. Brad Hacker just last year published in effect a continental growth, or at least how the continents might in fact interact with that subducting sediment in a fashion not previously conceived by either the folks looking at seismic sections through erosive arcs or people doing continental growth models. So Brad Hacker.